Hi, I'm Casey Klarman, and this is my lab number 4 for physics, focusing on oscillations. The purpose of this lab is to investigate the motion of a spring mass system with a mass oscillating in an ellipse rather than bouncing up and down. Using Tracker, we plotted the movement of the system and put the x and y values into a spreadsheet from the recorded Tracker data. The result of this experiment showed that the total energy of the system remains constant value of 0, demonstrating the energy principle. The fundamental principles we used in this experiment was Newton's second law, or the equation shown, the energy principle, which is the energy of the system is equal to the work done by the surroundings plus the heat, which is equal to 0. So for this, the total energy of the system is just the change in kinetic energy plus the change in the potential energy of the spring plus the change in potential energy of gravity. We also use the update formulas for our model, which is the final velocity is equal to the initial velocity plus the net force divided by mass times the time increment, and the position update formula, which is the final position is equal to the initial position plus the found final velocity times the change in time. And then the energy formulas, which is the kinetic energy is equal to 1/2 mass times velocity of the object squared. The spring potential energy, which is negative 1/2 spring constant times the displacement from the relaxed position of the spring squared. And then the potential energy of gravity, which is equal to mass times the gravitational acceleration of the Earth times the change in height. The initial conditions is our system is just the spring mass object, and we know that the mass is released from rest, because it's told us in the video, and there are no surrounding forces acting on the system. The mass of the object is given at 0.402 kilograms, and the initial position is negative 0.12 meters in the x direction and negative 0.64 meters in the y direction from our axis. The observed motion of the object in Tracker looks like this. Recorded data and our constant calculations. So from the graph given to us by the Tracker data, we found the period of our oscillation by using the y side of it and finding the distance between 3 of the points and averaging those together to where we found that our average period was 1.52 seconds. And from there, we used another calculation, which is the period is equal to 2 pi times m times the square root of mass over the spring constant. So plugging in the values, we found that our spring constant was 6.8872 Newton over meters. And for our relaxed length of the spring, we know the displacement is 0.7 meters, as given to us in the video. And then we know that relaxed spring is equal to the displacement minus the force of gravity over the spring constant. So plugging in for values, we find that the relaxed length of the spring is 0.1261 meters. Here for modeling the motion with our initial conditions, we plugged in everything we were given, with the mass being 0.402 kilograms, the initial position of the ball being what it is. We know that it's released from rest, so there is no velocity. We know that our gravitational constant is 9.8, the gravitational acceleration is 9.8 meters per second squared. The spring constant, what we found, 6.872 newtons over meters. The relaxed length of the spring is 0.1621 meters, and for our L value, we take the position of the ball, minus the position of the spring to find the length of the spring, which is when it's stretched. Our L hat is that length divided by the magnitude of the length to give us the unit vector for L. The stretch of our spring is the magnitude of L minus our relaxed length, so how far it is stretched. And then we plugged in these values for the values we found in our kinetic energy, gravitational potential energy, and spring potential energy. And then the sum of all those being our total energy as seen in the fundamental principles. And here we have the prediction part of this. We plug back in our initial values that we found above. We know that the force due to gravity is just mg in the negative y hat direction. We know that the spring force is going to be acting along the L hat unit vector, and we know that it is negative k spring constant times s. We know that F net is going to be the sum of those two forces, and we know that then we use our velocity update formulas and our position update formulas in the next part. And then we update the spring again with the same equations that we used above, and we updated the energies again, and then finding delta k, we just found the new k minus our initial k, and did that for each, and then we found our delta E to be, or our E to be the sum of all of these energies, and then delta E to be the new energy minus our initial. Here is the motion we observed, or we modeled. As we can see, it doesn't differ very far from our model to our experiment, but some of the errors that could have occurred to change the model versus the experiment a little bit would be a center of mass not being placed correctly in Tracker, the model not factoring in the loss of energy due to the surroundings. So like drag, causing the spring mass to slow down. And then the frame rate in the video is slower than the model, so some of the points aren't exactly in the right spots for the experiment. The curves aren't as correct. And then the question, is the energy principle satisfied? Yes, because no external forces act on the system, the change in total energy should be constant zero, which is shown in this graph. While the potential energies and the kinetic energy is changing, all of its energy is internal to the system, so the total energy of the system should remain zero. Thank you.